Good morning, good afternoon, or good evening. Hello, my name is Ms. Hernandez, and thank you for joining me for section 7.9 polyatomic ions. All right, and remember, everything that you see here in your packet is exactly what you will see in this presentation. Have you ever read the story of Romeo and Juliet? You probably have heard it, you've probably seen the movie, you've probably seen the play, right? It's usually required reading for one of your English classes. But Romeo and Juliet, who's going to help me with the introduction?
Shakespeare once wrote a rose by any other name would smell as sweet. Part of the romantic balcony scene between Romeo and Juliet and the play of that name. The two families were bitter rivals, but Juliet was saying she loved Romeo no matter what his name was. Some names are simple. We know Romeo mainly as Romeo. Most have a first name, middle name, often not used, and last name. In some cultures, name will be much more complex. The full name of the famous 20th century artist Pablo Picasso is Pablo Diego José Francisco de Paula Juan. ¿Qué dice ahí, Miss?
Nepomuceno.
María de los Remedios
Cipriano.
De las Santísimas Trinidad, Martir, Patricio, Slito, Luis, y Picasso.
Imagine that. I don't know about you guys, but some of you guys have really easy names that I can easily remember. Mario Chapa. I can remember that all day long, right? But there's some people who have more complicated names, right? Yalexia has, that's not a very common name. And she probably has a middle name in there too. For me, my name, people call me D. My friends and my family call me D. My real name is Delinda Yvonne Hernandez. And now that I'm married, I need to throw in there Garza. Complicated, right? Look at that. Yalexia is like Yalexia Nicole Alvarado. And then when she gets married, nombre. So, just like people can have simple and complicated names, the same thing can happen with compounds. Names and formulas become more complicated depending on the type of compound you're looking at or you're dealing with. Okay, and that's what we're going to be talking about today. We're going to most of Monday and Tuesday earlier in the week, we were talking mostly about binary ionic compounds, right? And we usually said that a binary ionic compound consists of two elements, right? The cation and the anion, right? And you only had one cation, right? One element as your cation, and you had one element as your anion. Today we're talking about polyatomic ions. So polyatomic ions, well, what do you think? What is the poly? What do you think the prefix poly means? Oscar, when you hear that word poly, what comes to mind? Okay, and I'll give you a hint. When we were working with binary compounds, Monday and Tuesday, remember, we said that there's a cation and an anion, meaning there's just one and one, right? One cation, one anion. What do you think polyatomic ion means? Oscar, are you there? Irvin, what do you think? You're there, right? Oh, there we go. What do you think about polys? The prefix poly, what do you think it means? The prefix bi means two. The prefix tri means three. What do you think poly means? Anybody out there? What do you think poly means? A lot, right? Definitely more than one. Great job. Yes, that is true. The prefix poly means that you got more than just one. Okay? So our ion, instead of the cation or the anion just being one element, you're going to have more than one element for these guys. Okay? That's what polyatomic ion means. All right? And our reference sheet, in our valence sheet that you see here, you might have to come back to Google Meet to see this, guys. In your reference sheet, if I zoom out, trying to zoom out. Oh, you'll notice, remember yesterday we were just working with column 1 and the top half of column 2. On the second half of column 2, that's where you're going to find your polys. Look at that. Up here, it was just one element, right? Once you get to the second half, let me zoom in. All of a sudden, these ions have more than one element. That's what we mean by polyatomic ions. They are small compounds that have a charge. Okay, yesterday was all about elements and their charges. Well, this time we have more than one element, but they still have charges. Okay, so you're going to have more than one element, so you're going to have more than one chemical symbol, and you definitely might have some subscripts in there. Okay, so you got some extra letters, extra numbers in comparison to what we were doing yesterday. Many materials exist as simple binary compounds composed of a metal cation and a non-metal anion, with each ion consisting of only one type of atom. Other combinations of atoms also exist, either larger ionic, complex, or complete molecules. Some of the most useful materials we work with contain polyatomic ions, and they're giving us 2 examples: baking soda and antacid, right? Antacid. Antacid is like when you have acid reflux. As you get older, you might develop this. You know, you guys are really young. You might not be experiencing acid reflux, but us older, people, like me and Ms. Garza, we're a little bit older. We, depending on what we eat, especially if it's spicy, or it's got a lot of spices, you might get that acid reflux, and we take some Tums or antacids to help control that. And if you look here, there's more than 2 elements. More than likely, there is a poly in here. I call polyatomics polys. All right. In baking soda, right? Baking soda we use around the house to control odors. Baking soda, look at that. NaHCO3. There is definitely a poly in there. All right. So what is a polyatomic ion? A polyatomic ion is an ion composed of more than one atom. The ammonium ion. So they're talking about the first example, ammonium ion consists of 1 nitrogen atom and 4 hydrogen atoms. So definitely more than one element. You're going to have some subscripts in there also. Together, they comprise a single ion with a +1 charge and a formula of NH4. And it's got a little plus for that +1 charge. So you got definitely more than one element. You got definitely subscripts, and then you have your charge. Okay? That's your first example. Your second example is found in the calcium carbonate, in that acid reflux medicine that we take. The carbonate ion consists of 1 carbon atom and 3 oxygen atoms and carries an overall charge of -2. The formula for carbonate is CO3 with a -2 charge. Again, more than one element, a subscript, and a charge. The atoms of a polyatomic ion are tightly bonded together, and so the entire ion behaves as a single unit. So it's very similar to what we were doing yesterday, but this time we're going to have more than one element. There's going to be a subscript in there, but you're still going to see a charge at the end. Okay? So it is very similar to what we did yesterday. So here, don't forget, a polyatomic ion is a small compound made up of more than one atom and definitely has a charge. Okay, keep that in mind. All right, those of you in periodic, what is a polyatomic ion? Okay, what do you remember that we said is a polyatomic ion? Please type in your response. If you are not in periodic, you should be answering on the Google Meet chat. You should be answering on the Google Meet chat. Come on, people, talk to me. What is a polyatomic ion? All right, I got 1 out of 7 students responding. What about my other 6 students? What you guys doing? Come on. What is a polyatomic ion? What do we say? What will you see? Melissa, are you there? What is a polyatomic ion? Irvin, are you there? What is your version or your definition of a polyatomic ion? Let's see if they're done writing. All right, it is a compound mixed with more than a lot of elements, right? There's definitely more than one element in there. Great job. Great job. Thank you so much. All right, we got some more examples and models of polys. Picture A, the ammonium ion, NH4 with a positive 1 charge, is a nitrogen atom in blue bonded with 4 hydrogen atoms. All right. So here you can see in blue in the middle is your nitrogen. At the top, you got your hydrogens, right, at the ends of this compound in white. The picture B is your hydroxide ion, OH with a negative 1 charge. You have oxygen in red bonded to hydrogen in white. The third picture is carbonate, is your carbonate ion, CO3 with a negative 2 charge. You will have your carbon in the middle in black, surrounded by red oxygen atoms. Okay? More examples. Which of these represents the ammonium ion? A, B, or C? A, B, or C? Which one represents the ammonium ion? What you think? Who's got the answer for me on this one? Melissa, Arlette, Yoselin, what do you think? A, B, or C? Which one is ammonium? Again, there's only one person writing. Irvin, what are you doing, Irvin? You're not paying attention. Mario, A, B, or C? Which one is ammonium, according to what we discussed in the last slide? Efrain, Jose, Hania, what do you think? Mario thinks it's letter C. Okay, what else? Who else? Anybody else have a different answer? Oscar says C. Anybody else? Alexia, C. That is correct. Letter C is ammonium. Great job, guys. Good. Great job. All right, so now we got a picture. This table lists a number of polyatomic ions by name and by structure. The heading for each column indicates the charge on the polyatomic ion in that group. Note that the vast majority of ions listed are anions. there are very few polyatomic cations. All right, so most polys you will find at the end of your compound. There are a couple that you will find at the beginning, but they're very easy to spot because there's a few of them. In this picture, they tell you on the right, over here on the top right, that you have ammonium as one cation and dimercury as your second cation. Okay? On our list in our reference material, we only have ammonium and ammonia. NH4 and NH3, both of which have a +1 charge. Okay? They're very few. They're easy to spot. Okay? They're very easy to spot. All the other polys are considered anions. They all have negative charges. They will always come second in your compound. Okay? There's some polys that are on this list that are not on our list that we have in class. All right? In case you run into a poly that's not on this list, let me know and I can give you the information you need to complete the question. Okay? Just as an example, let's see. Silicate is definitely not on our list. Silicate. I don't think arsenate is also on the list. I think everything else is just about there. And of course, I already told you that dimercury is not on there. Oh, peroxide, I don't think is on there either. I don't think peroxide's on there. Oh, no, it is. Okay. All right, but there are a couple that are not on there. All right, so I'm going to assign A, B, and C to different students. So pay attention. I'm going to be telling you which one you're going to be doing. For letter A, I'm going to give that one to Mario. Letter B, Yalexia. Letter C, let's give that one to Oscar. And letter D, I want Melissa. Melissa needs to earn her extra credit. Melissa, be prepared. You will be presenting and giving me the formula for letter D. So A, I believe I give it to Mario. Yalexia B. C is Oscar. D is Melissa. Give me the formula according to your reference sheet right here. Okay? You can type it on Pear Deck and then you can put it into Google Meet. My aunt's having surgery, so I just want to make sure she's okay. She is out of her heart procedure and is in recovery resting. Oh, that's good. Thank God. Everything is well and she will be released about 6 this evening. Oh, thank God. Everything's great. I'm scared for her. But God is good and he helped her through it. All right. Oscar's ready to present his. Melissa's ready to present hers. Excellent. All right. Let's go back to the Pear Deck. Let's see what people wrote. Oh, no responses on Pear Deck. Okay. Oscar, you had letter C, nitrate. Nitrate, if you look on the list, and nitrate right here. NO3 with a -1 charge, exactly the way Oscar wrote it. Thank you, Oscar. Melissa, she went ahead and she was doing letter D, nitrite. If you look on the list, nitrite comes right after Oscar's nitrate. I don't know. I can't. Okay. What if I do that? Here we go. Right here, nitrite, NO2 with a -1 charge. Great job. Thank you, Melissa. Excellent job, mija. All right. Anybody else? Mario, you were supposed to do cyanide. So look for cyanide on this list. Cyanide. Not that one. That's chrome. Oh, right here. Cyanide, right? Cyanide. Cyanide right here. CN. Very good, right? CN right here It's got a -1 charge. Excellent. Great job, sir. Great job. All right, Alexia, you were doing hydroxide. Hydroxide. There it is, isn't it? There's hydroxide, Alexia. What's the formula? OH. What's my charge? -1. There it is, guys. Right there. Hydroxide. All right. Today is just naming. What's the name of them? What's the formula for them? That's all we're doing today. We're doing the easy part. I need to show you this before we move on to the rest. Hide cursor will not move. Okay. Great job, guys. Anions. Okay. Let's back up. Okay. Anions. The vast majority of polyatomic ions are anions. Okay. So if you noticed, the one that Melissa and the one that Oscar did, look at those formulas, guys. They look practically the same. The vast majority of polyatomic ions are anions, many of which end in either ATE or ITE, ate or ite. Notice that in some cases, such as nitrate, NO3 -1, and nitrite, NO2 -1, there are multiple anions that consist of the same two elements, right? In this case, nitrogen and oxygen, right? In these cases, the difference between the ions is the number of oxygen atoms present. While the overall charge is the same, as a class, these are called oxoanions. Oxoanions. And on our reference sheet, it's actually oxyanions. Why? Because most of them contain oxygen. When there are two oxoanions for a particular element, with the one with the greater number of oxygen atoms gets the suffix ATE, while the one with the fewer number of oxygen atoms gets the suffix ITE. The 4 oxoanions for chlorine are shown below. All right, so we're talking about chlorine bonded to oxygen. There's 4 different versions of those, okay? In the case that you have one, okay, so all of them are going to have one chlorine. The only thing that is going to be changing is the number of oxygens. When you have one oxygen bonded to chlorine, it's going to be known as hypochlorite. If you got one chlorine and 2 oxygens, that anion is chlorite. Sorry, did I say hypochlorite for the first one and chlorite for the second one? In the case of 1 chlorine and 3 oxygens, that's chlorate. And if you have 1 chlorine and 4 oxygens, that's now known as perchlorate. In cases such as this, the ion with one more oxygen atoms than the ATE anion is given a per prefix. The ion with one fewer oxygen atom than the ite anion is given a hypo prefix. All right. All right, we're going to watch some of this video. Okay, we're only going to watch about 5 minutes, and I'm going to skip around because there's some things that she goes over that we're not going to talk about today. No commercial. Come on.
Hi everyone, Miss Sheehan here. Today we're going to learn how to write and name
No. What's going on?
Compounds with polyatomic ions. It's very similar to video 2, where you named how to write and name compounds. Some ionic compounds contain polyatomic ions. Polyatomic ion.
Who buried me?
So, some ionic compounds contain polyatomic ions. Polyatomic ions, if you remember from last chapter, is groups of atoms that are covalently
I don't know why it looks like that. It was fine earlier.
bonded and have a charge. Those groups of atoms have either gained or lost electrons so that the central atom gets an octet, as well as every other atom, with the exception of hydrogen. If you remember, hydrogen gets a duet. So these charged groups of atoms.
Trying to fix that. I don't know why it looks like that. Okay, there we go.
Are anions.
Okay, here we go.
That means that they are negatively charged. Most of these are actually called oxyanions because they contain oxygen in their structure. Sometimes a group of elements can form more than one oxyanion, which means it's got more than one name. So here's a chart that I gave you in class of some of the common polyatomic ions. If you notice, some of them, such as NO2, which is the 6th or 7th polyatomic ion in the right-hand column, has a name of nitrite, where NO3 has a name of nitrate. You know, that happens for several of these compounds, two elements, one of them being oxygen, making more than one polyatomic ion.
Sorry it looks so bad, guys.
If you notice on the very far right side of your screen, there's only one polyatomic cation, and that's the ammonium ion. It's got a +1 charge. So we're going to use these polyatomic ions to create ionic compounds. So what's up with the 8 and the 8? The PO4 minus 3 and the PO3 minus 3. If you noticed, we had, just like I did with the example with the NO2 and the NO3, there's one less oxygen in the PO3 than there is in the PO4. The greater number of oxygen atoms ends in 8, and the lesser amount, the fewer amount, ends in 8, which is perfectly acceptable. I'm not going to have you remember that. I just wanted you to know why the difference. Okay, one has more oxygen atoms, one has less oxygen atoms. Use your charts, look these up, and name them. I want you to become very familiar with the polyatomic ion chart that I gave you. You have NO3 minus 1 charge, SO4 minus 2 charge, SO3 minus 2 charge, and NH4 positive 1, the only polyatomic cation. So when you're done naming those, you can bring them in and we'll talk about them in class. Let's learn about writing formulas with polyatomic ions. You got to look at the ions and balance their charges to create the formula. If you remember, all formulas are electrically neutral. The easiest way to balance charges is to crisscross them. If there is more than one polyatomic ion in the formula, we want to put parentheses around it and the subscript for the polyatomic ion on the outside of the parentheses. For example, magnesium with a +2 charge and phosphate with a -3 charge. We put parentheses around the phosphate, crisscross the charges, you'd end up with Mg3, PO4 in parentheses, 2. So let's look at how I got that. There's your 2 polyatomic ions. Well, there's your 2 ions. One is polyatomic. Notice the 2 and the 3 are in red, they're in yellow. We're going to crisscross those charges to get the formula, Mg3PO42. Now, let's try another one. We got potassium with a +1 charge and nitrate, NO3, with a -2 charge. Same thing. You've got 1 and 2. You want to crisscross those charges to get the formula K2SO3, 1. You don't need to write the parentheses.
So the one thing that's really, really new is the fact that you're putting parentheses around the poly. You still identify the symbol and the charge. If they are the same number, those charges, they cancel out and you just write the letters and numbers together. In the case that you do cross down, the poly must be protected from the number that crosses. We protect it by using parentheses.
Parentheses or the number 1 if there's only one polyatomic ion. If you feel more comfortable writing it as you're getting started, I have no problem with that. But recognize the fact that if there's one polyatomic ion, you do not need the parentheses. I want you to write these formulas tonight, and we will go over them for homework. Okay? Now, how about naming ionic compounds with polyatomic ions? Well, just like in monoatomic ionic compounds, you name the cation with the element's name. Name a monoatomic anion by changing the ending to "ide."
Okay, we're going to stop there. I don't want to get you confused. All right, exit out. Polyatomic ions contain more than one type of atom in the ion. The majority of polyatomic ions are anions that are name ending in ATE or ITE. Some anions have multiple forms and are named accordingly. So you might see ATE or ITE. All right, these are your formula, your review questions. And thank you for listening, those of you on watching the video. We'll see you soon. All right, guys, let's go to our electronic version. Let's see if we can do 1 and 2 real quick. All right, Oscar, letter A. B, Alexia. Letter C, Mario. Letter D, Melissa. Okay. So Oscar, Alexia, Mario, and Melissa. Ammonium. Oscar, what's the formula for ammonium according to this list? Oh, hold on.